All right, in this last section of chapter 6, we are going to use our integrating skills, okay, to calculate the average value of a function. So what I said in class and what I'll say here in the intro is a good analogy is the car driving at different speeds to get to San Diego, arriving at a certain time, and then the driver calculating his average speed during the trip. Well, we can do that. We can do that with any function whatsoever. It doesn't have to be speed or anything like that. So this is looking kind of small, so that's better. Okay. Okay, so in this section we talk about the mean value theorem for integrals and the average value of a function. Okay, so let's get to it. A geometric argument for the mean value theorem of integrals looks something like this. So first of all, here's the theorem right here. Let f be a continuous function on AB. All right, let's draw a picture. All right, so this is A and this is B. And our function might be doing whatever it's doing, call it f. Okay, and we're interested over this interval for the average value of the function. The way you do that, if you think about the car drives a certain distance, okay, and think of this maybe over here to the side. I mean, his speed might vary like that. But when you integrate over a velocity function, that area is your distance. Logically speaking, we can also think of that as, well, you know, what if he were able to, or she was able to go at a steady clip the whole time, I'd cover the same distance at the steady speed. That's what we're trying to do, is we're trying to come up with a way to find the average value, okay? So integrating under the green curve is the same as integrating under the straight line for the rectangular area, and that happens if you've got a continuous function, you're able to do that. Let's just get away from velocity for a moment, and let's play this game of finding a rectangle, okay, whose area from A to B, okay, is identical to the area under the actual curve itself. So the area, the big green area, you know, what you've got is, okay, here's this area underneath. But what we're going to do is we're going to slide a rectangle under it, and we're going to go up just high enough. I don't know where it's going to be. It could be up, maybe up here. I don't know. It could be down low. Let's say it's down low. And if you cruise all the way across and down and compute the area under that rectangle, let's say it's exactly the same, okay? There's two things that we do. What we do is we find the actual, what they call the average value of the function, which is here. This is what they call FAVE, which is average. And then, we're not done. We actually look for a value C in AB whose function value is equal to that guy. So f of C is equal to f average. But here's the funny thing about it, okay? If these two areas are identical, that is to say, if this rectangular area, okay, is equal to this other area under the curve, okay, so I'll draw, do my best. Okay, if these two, and shorten it there like that. If these guys are equal in area, well, the area of this guy, watch this, the area of this guy is f average, whatever that is, and it's equal to some sort of C evaluated by the function. So it's got this side, and it's got this width. So the area, what is that width, by the way? Let's look up here. Oh, it goes from, oh, it's B minus A. So this side here is B minus A, okay? So on this side, what we have is F average times B minus A, or whatever that C value is at times B minus A, is actually equal to the area under the curve, which is calculated integrating A to B, your function f of x dx. Without, I'm not proving it, but what I'm showing you is for me, that convinces me if it's a continuous function, we can do this thing, okay? So if you look at the theorem up above, let's see, where are you? There you are. If you look at that thing, it says we've got the following. That's what we just established, is the definite integral from a to b of f of x is equal to some f of c times b minus a. But that also leads to this. F of c equals 1 over b minus a times that antiderivative, or that definite integral, is called the average value of the function. So the average value would be driving the green speed, okay, fine. But what if we drove the red speed the whole time? We get there the same time. The average value, there you go. Okay, so I'm going to work through a problem from the homework over here. And it has us do all this stuff. Actually, it's not from the homework. I made it up. It says, let's play around with f of x is 4 minus x squared on the interval minus 2 to 2. It would be nice if you got an idea of what that guy looks like. I think I did it right. What I've got is a curve that goes up to 4, but drops down. You know what it is. It's a parabola doing its thing. Okay, and it hits its minus 2 here, and the 2 here, and of course it keeps going. Okay, we're going to play this game of average value and all that stuff. You ready? Let's do this. So number 1 says, find the average value of this function over the specified interval. Hey, Weber, yeah, scroll back up. Okay, what do you want? I want to see the average value. Oh, yeah, there it is right there. Okay, it is, I'm just going to calculate it. I'm going to call it f of c. I'm going to say, all right, I'm going to go 1 over b minus a times this integral. Let's do this thing. Okay, and I'm going to do some intuition as I go through it too. So the average value, f average, if you will, is going to be 1 over b minus a integral a to b, whatever your function is, dx. Okay, for us, in this problem, f average is equal to 1 over 2 minus a minus 2. That's the width of the interval, right? And integral from minus 2 to 2. And if you want to use symmetry there, you can, but be careful. And our function is 4 minus x squared dx. So let's get to calculating, okay? It's the same as the integral, except you're dividing by the width of the interval, okay? So 1/4, and we're going to integrate right away. We're going to get 4x minus 1/3 x cubed from, what, minus 2 to 2. Okay, so we've got 1/4. We're going to put in, first of all, we'll put in the 2. So we've got 8 minus 8/3, right? 2 times 2 times 2. And then minus, now we're plugging in minus 2. It's a minus 8, right? If I plug in a minus 2 there. And here it's a minus 8, and then minus is plus 8/3. And there's that symmetry. If you doubled it, you'd get the same answer. Okay, but we still have that 1/4 out there. So f average is equal to 1/4. And in here you got 8 and 8 is 16 minus 16/3. You know what? They're divisible by 4, so I'll write this as 4 minus 4/3. I did it weird, didn't I? I distributed the 1/4. Why not? And so this is actually a common denominator. 3 would be 12 minus 4 is 8/3. Okay? Same as, what is that? 2 and what? 2 and 2/3? Okay. All right. That's step 1. We did it. The average value of the function is 8/3 or 2 and 2/3, whatever you want to say. Let's go to problem 2. All right, it says 2. Find a c value such that f of c is equal to f average. So we're trying to figure out, find c such that f of c is equal to f average, the average value. So there's a c somewhere between minus 2 and 2 that does the game. All right, and I'll draw the picture later and then we'll talk about it. So what we typically do is you take your function, which is what? 4 minus x squared. F of x is 4 minus x squared. So f of c is, of course, 4 minus c squared, and you set it equal to 8/3. Okay? All right. So if we do that, what we do, well, let's see, I'll throw the c squared on this side, and over here I'll go 4 minus 8/3. And of course, that ends up being 4/3. Doesn't it? 4 over 1 minus 3 minus 3. Yeah, okay, so therefore, c actually ends up being the square root of 4/3. But wait, plus and minus. There's two choices. So we're getting c is equal to, say, plus minus 2 divided by radical 3. And that's it. You found them. There's two of them. Why? Well, step 3, sketch the graph with the rectangle. And this is the best part as far as, I just love geometry. I got this picture in my head right now. So I got this going on, and the curve is drifting down, let's say like so, and this is up at 4, minus 2 and 2. And what we're going to do is get that rectangle in the picture now. We're going to go up to, what did I say, 2 and 2/3? Not 3, but 2/3. And we're going to extend outward this away and down and down. There's the rectangle whose area, it doesn't look good, my picture's terrible, okay? Just never mind that picture. I think the parabola is skinnier than that. We're going to leave it alone. We're pretty good with that. And not only that, but we found, let's do this in another color. We found the C, there's one, and there's another, where, you know, the one on the left is -2 over radical 3. So if you plug in that number, you go straight up, and that guy is the average, that is the average value, that is the C that causes or conjures up the average value of the function. And over here is the other guy. Okay, you have one problem like that, and this is what we're looking for, is understanding the geometry and also how you find these specimens. That's it. I hope you enjoyed that one. See ya.